Good afternoon, and welcome everyone to the first session of the SIG in DSD series, proudly organized by Spark. We're starting this series at a very interesting time. A few years ago, learning Verilog or VHDL meant hours of scoring through datasheets and debugging syntax. Today, you can ask a chatbot to write a finite state machine for you in just seconds. But does that make us better engineers or just better prompt designers? As ENTC students, we need to ensure our foundations in digital design and FPGA technologies are rock solid. To help us navigate this new landscape, we have S.Thuvaragan from the ENTC 21 batch here to talk about learning digital design at the age of LLMs. Let's dive into how we can actually use these tools to master FPGAs without losing the fundamental skills. Tua, the floor is yours.
Hello. Can anyone confirm whether I am audible? Hello.
Yes, Tua,
All
we
right,
can hear.
cool. Thank you. Yeah, so uh, it would be good like if everyone can join to the slide, or I think you can scan the QR code as well as enter the code in the slido.com in order to join that. Like I will be able to gather some insights from the crowd so that I can better guide you guys through like what previous experiences you guys have had so that I can like give you guys a better understanding of things. So if everyone can join the Slido and like answer the things, it would be good. Yeah, so I guess we have people in the room with Python and C++ experience. I mean, do others do not code anymore, or like what's going on? I mean, you don't necessarily have to code anymore. Yeah, like everyone is using agentic LLMs now, but still people will have choices about what sort of programming languages they want to use, right? So you can express your own. Uh, People don't have some certain preferences either. Yeah, that's appreciable as well. All right. So I'll make this question more specific now. So it's fine. Like you can keep your favorite programming language to yourself. You don't have to tell me. Keep that a secret with you and your ChatGPT. Yeah, let me know this one now. Like, what's your favorite HDL? I hope everyone in the room has heard of HDLs. If not, uh, I don't think you might have joined this session. If you haven't heard of HDLs, please do some sort of reaction in the Zoom meeting or somewhere else, or just mention that you haven't heard of HDLs. But yeah, what's your favorite HDL? Like, favorite is a loaded word here. Like, I don't, I haven't seen anyone use an HDL uh, by favoritism or like by desire. Most likely being forced, and yeah, they haven't tried anything else because the curriculum doesn't include anything else. So yeah, that makes sense. Yeah, we have some VHDL people here as well. That's quite interesting. People who have VHDL as their favorite language. Yeah. All right. It seems like Verilog is the most uh, used HDL, or like the most curriculum friendly HDL from the crowd here. Yeah. Anyways, and now we are going to move to the next question, which is what sort of agentic tools have you guys used? Like whether it's VS Code and Copilot, or Copilot CLI, or Gemini CLI, or anti-gravity. I hope you guys have heard of something like this, or there are open source harnesses like OpenCode, PyAgent, and uh, yeah, there are plenty of agent harnesses. I see. Like most people use Copilot. I'm guessing Copilot means you guys are using Copilot with uh, yeah, Cursor is also there. Copilot with VS Code. Yeah, that's cool. That's cool. All right. So that's yeah. So we have a like moderately general population here who has used like uh, most common tools that are generally market popular and generally good for all tasks considered. So yeah, there are people who have used Gemini, Cursor, and anti-gravity as well. Yeah. So these tools are like generally acceptable for all common tasks. And we are a special interest group, right? So let's dive into what we have in store today. Mm, uh, Give me a moment and hope everyone can see my slides, right? So now we are being slides. Before we move in, for those of you who don't know me, I don't necessarily advertise, at least in a sense, but I'm Thuvaragan, and you can know more about me in this website. I am a final year undergraduate, uh, and who most likely involved with FPGAs and ASICs and those sorts of workflows, and generally interested in LLMs nowadays because, yeah, obviously you have to work with them, otherwise you are going to get left behind, right? So I'll give you guys a hint of what I have learned through and what you can focus on. And I'm assuming not everyone has a detailed knowledge of HDL, and you are not expected to have any detailed HDL knowledge. That's what we are here for. So we'll be covering why DSD is notoriously hard. Like we'll going, we will be going through some of the observations that you guys have already seen through and learned through, and why LLMs and tools matter now, and what are the better ways to learn DST. Some of you might have been utilizing these things early on as well, but it's better that everyone is on the same page, and I might be able to provide you with some extra insights. And yeah, setting up local DST labs, which is some of the things that we are currently only recently being able to do. Like there are people who have been doing these sorts of things for a long time, and it has been hard, but it's relatively easier nowadays because of LLMs and stuff. So we will be covering that as well. And what are the emerging tools related to DSD and LLMs and the industry standard tools that you guys will have been using for certain labs and experiments, and where LLMs fail bad and how to avoid those, and where LLMs help and how you can better utilize them, as well as some workflows and techniques to manage these things overall. We won't be covering HDL or digital design fundamentals because this is not the talk for it. Uh, because nowadays there are plenty of learning opportunities for you guys. We will be going through some of them as well. So learning is self-help from these times as in modern times. So it's expected that you have to learn yourself, and you have plenty of tools available that you can learn these things in a better way. And fundamentals are very important, so you don't have to skip them. And then another thing that we won't be covering that is relatively very important and adjacent to DSD is compilers and ISA. So as far as when you are considering developing a digital system design that's covering processors or very high performance compute, something related to that, then you will need the knowledge of compilers and ISA as well. It is an adjacent subject and tangent to what we cover in DSA most of the time, other than when you are trying to do some analog designs. But yeah, that's something we won't be covering today, but you'll have plenty of opportunities to learn them as well. And the legal implications of LLMs, which is a gray area nowadays because of everything that's been going on and how industry is treating existing source code and existing copyrights, right? So that's a rabbit hole that we won't be going into today. So why DSD is notoriously hard? So these are some of the memes that in a Reddit I gathered from the Reddit thread, which is famous for people who are dumping on Vivado and not really dumping on people expressing genuine concerns over how DSD tools have been over the few years, right? So the tool chains are notoriously difficult to handle, especially in the DSD domain. If someone has handled Vivado, they could have seen like hundreds of errors and warnings that are being output. As long as you don't get a critical error, you can proceed with the code and Vivado won't give you any guidance as to whatever. And it's partly because of the language ecosystem that has been developed over the 50 years. Verilog and System Verilog, everything building on top of each other, inheriting all the foot guns and everything that C++ even had in the language design itself, and then building upon itself. Verilog borrowed the syntax from C++ and then built on top of it. And then even though there are some bad design choices, because we need to have backwards compatibility and legacy support, they also kept that and added new features on top of that. And there are a million ways to do one thing, which cause these kinds of issues, right? So that's why DSD is notoriously hard to learn, because one of the first ways you learn DSD is by drawing an architecture diagram and then trying to convert it to an HDL language, right? So that in itself gives you a headache, because the teacher will, the lecturer will give you an idea about how to do that in the HDL. But when you try to do it, you will get all those warnings and stuff, and then you have varying levels of abstraction that you have to deal with, right? So these tools are the main problem that people have had when learning DSD, right? The HDL and the tools. And now we are going to see how language LLMs can make this easier, and how we should be careful to use them, right? So this is something general when it comes to all LLMs, right? We will go through that later as well. So let's go into why this matters, right? So one thing is, as I have showed you earlier, tools have been notoriously bad, right? And the biggest issue is those tools were closed source. If you say Vivado, you will get free trial for Vivado. If you have Questa, you will get free trial for Questa, but you have no way of controlling their workflow, right? They have notoriously bad GUI for years and bad workflows that have been kept inherently increasing in complexity as they improve their workflow, right? They have to keep the old workflows and new workflows and everything else. So this has been one closed source problem as well as increasing complexity problem. And the open source community has been working on new tools that are open source and can be handled by community over the years. And those states have improved. And this is allowing us to make better choices nowadays. And I will show you that we still have to use Vivado, but there are better ways to use Vivado and better tools alongside Vivado that will give you a better edge when you are trying to learn or doing a serious project. We will go through that. And the next thing is LLMs. So you are no longer limited by the choice of HDL, which is the main thing, right? So whether you are going to choose the Verilog or the system Verilog, or there are plenty of other HDLs. If anyone is interested, you can contact me later as well. Like there are Python based HDLs. There is a Scala based HDL called Spinal HDL, and there's a Rust like HDL called Spade. And then, yeah, there are plenty of HDLs out there. That's the gist you have to learn from here. And you can choose any of them. You don't have to learn the whole syntax. You just have to know the fundamentals of digital design, like how the architecture works. And then you can construct the architecture in your specific HDL, right? So that your mind map can map to the HDL in a better way. And the syntax and everything else will be handled by the LLMs. That's one benefit, right? And the next one is instant help for syntax logs and boilerplate and explanation. So if you are not like not figuring out why a specific syntax is being used at a certain place, which is useful for when you are trying to learn Verilog as well, this is an important thing because you don't just prompt the engine to write a Verilog file for you. You have to learn to write at least a basic HTML file. Otherwise, you will forget how to start writing a file as, which is an important thing because not every interviewing process has changed to accommodate LLMs, right? So people still check that. So that's an important thing you have to keep in mind. So that's the ally. You have this plenty of help available for syntax logs and boilerplate, like getting started with a project and setting up a project. So you have to make sure that you know the important things and is able to do them, and then set up a workflow to automate them using LLMs. Just don't prompt the LLMs to do everything, because that way you will lose your flexibility as well as your knowledge inheritance as well. And the next one is sort state of the art models, right? So these models can learn tool usage and adapt on the fly. Like, even if you are introducing a new simulator that is currently being updated by the community, you can just tell the LLM to read the manual of the tool or try to run the CLI tool in the bash and learn how to use it. The model can produce a guide document for yourself and for itself by itself. That's one of the important things that the current capability of models has allowed us. This will help you learn the tool better as well as automating the tool later down the line as well. So this is what LLMs have enabled very recently, because uh, uh, if you look at the state of LLMs when it's a 1 year back, you see LLMs are very error prone. There are LLMs erasing whole JIT folders and version control systems, destroying databases. Like, tool tool call handling, which basically means LLMs are able to run commands on the terminal and be able to access tools in a better way. That has improved quite a lot in the recent times, and that enables us to handle this in a better way. That's the second point. And the third point is more like an overall view we have to keep for to make ourselves sane, as well as to motivate us to learn DSD, which is hardware monopoly. I hope everyone is aware of how NVIDIA has kind of like a monopoly on how the hardware chips are handled nowadays. I hope everyone is aware of that, because they are almost one of the biggest like revenue making companies because of the AI boom and how they are selling graphics cards, right? And no one is able to touch them on the hardware capability, which makes sense because they have been using these tools. I will show you examples of how now NVIDIA is integrating these LLM tools from 2024 or even before that. Like, I only know because it's documented and published as a paper, but there are plenty of in-house tools they will be using. So hardware is a scale that uh, when you are trying to do some complicated workflows, you have to scale with them in a better way. And LLMs allows you to scale, but still you have to keep fundamentals in your mind map. And that's why this is another important point that you have to keep in mind, because monopoly is something that's not good, even if you consider it in a general sense. So people are trying to catch up, and open source communities and open source ISAs are trying to give a competition to them and improving. There are still plenty of ways to go through, and even you can contribute. But this is another point you have to keep in mind to motivate yourself so that you can catch up or even exceed what NVIDIA has done in the hardware learning space. I hope that was clear. So before moving on to LLM workflows, I want to make sure that everyone has enough resources and an idea about how to learn the fundamentals, which is important because you don't have to learn every inch of HDL or every inch of DSD, which is quite an impossible task because there are plenty of foot guns and issues with HDL and DSD that we don't want to put our head into, right? So these are three categories I have made into. There are plenty of other things as well, but three things I want you guys to focus on, because this will allow you to better focus on things and not completely rely on LLM tools. Because one of the things people do nowadays is you go to ChatGPT and you search about a certain topic, and you believe everything it says. That's one thing. And then you believe that it has searched everything that there is. That's a big wrong assumption that we make. Like ChatGPT doesn't have access to the whole web search, right? Even Google doesn't have access to the whole web search. And there are plenty of URLs that are being ranked on the top because of the SEO optimization. And that doesn't necessarily hold true for valuable educational materials. So you have to know what resources you trust and what resources are exactly useful to you so that you can use other LLM tools to gather the information from the resources you trust and then based on them answer your questions or help with your learning. So these are the three tools. HTL Bits is one of the coolest websites that you can use to start learning HTL. Like even if you have worked with Verilog before, I would encourage you guys to go through this HTL Bits site and try to do everything manually because it will help you enforce the fundamentals of Verilog code. Like even if you don't write Verilog code manually by hand, it will give you an idea to inspect the code that is written by LLM, which is very important when you are dealing with LLMs, right? Because this will reinforce your knowledge on Verilog syntax and hardware description language syntax. Because if you are going to use LLMs, you will soon forget what Verilog. Trust me, I have forgotten Verilog because this will give you an edge over the others because it's a very easy to get started and you can quickly go through the exercises and brush up your memory, right? And the next thing is training webinars and YouTube. So one of the webinars I usually use is BLT, which is hosting no cost events. Like you have to register before all the seats fill up. That's one thing. But as far as I've seen, uh, I haven't seen seats fill up that quickly, but you still have to be interested. Like if you are dealing with Vivado or any sort of AMD FPGA, they have industry quality webinars scheduled all around the year. So you can register for the no cost events and watch them. Like you can register and even watch them at a later time as well. So it's a really convenient way to access industry standard knowledge from home. And then there is educationalchannels.com, which is basically quite useful website I found, which lists all the educational channels from YouTube so that you don't have to deal with the YouTube algorithm or the convoluted search algorithm of YouTube. So, and two of my favorite channels when it comes to FPGAs and digital design, I have also mentioned them. Hope you guys can get some use out of it. And then, of course, there are academia courses and blogs like edX and MIT's OpenCourseWare courses and blogs like Zip CPU and Project F has a nice list of recommended FPGA sites that you guys can check out. So for old school people or people who prefer going through blogs like me, you can use these links to learn, make them useful to yourself. Oh, of course, there are tools like Notebook LLM. I hope you guys have used this, which is quite a useful tool by Google. You can even search for resources via Google, but I wouldn't recommend it. I will encourage you guys to find your own references and add those links and videos here. And then you can basically search, summarize, do whatever you want with those resources, which is quite useful for any sort of learning thing you have to do. So that's the first step, right? Learning the fundamentals. Now let's assume that you have did this and you have set up this workflow and you are able to learn HTL to however you want at whatever pace you prefer. And once you have learned HTL, you have to apply it, right? So we have quite useful tools that not everyone knows of. Like I have my colleagues as well who haven't heard of these tools and had to deal with Vivado all the time, which is quite a heavy software and had an intensive startup time, which I don't usually prefer. So we need to have quick iteration cycle, right? So we need to get started and working immediately. So these are the three tools I'd recommend you guys to use because these emphasize the required skill set that you need to have in order to survive in the LLM assisted HDL workflow or digital system designs workflows that you guys would have to face. The first one is architectural knowledge, right? You need to know how an Verilog code transforms into an actual digital circuit. Can you guys see this? Can anyone respond? Is this visible for you guys? Cool. Mm, yeah, so this one is digital JS, and it's a quite useful tool that when you are writing a Verilog module or system Verilog module, you can go and paste your code in here, and when you click run, you are able to simulate that circuit in a visual form. So A and B adding, and the results we can observe. So that's the purpose of this tool. And I have found this tool to be quite useful for studying for my exams or like researching how Verilog actually works. Like you can change this code whatever you want, and you can use other primitives and try to see how it like influence how the components or the logic units are transformed into. So this is one of those tools that you have when you want to brush up your fundamentals or when you are trying to learn initially. This will help you to get started fast and also build up your intuition in a better way. And it's interactive as well, which is quite good, and it's online, so you don't have to install anything, but it's still an open source tool, so you can just clone it and build whatever you tool you prefer on top of it. I'm saying this because you guys are engineers. I'm sure you some of you will be interested in building on top of this tool to make it offline or make it more useful to some extent, right? So that's digital JS, right? And the next one is EDA Playground. I am not sure how many of you guys heard it. This is basically a tool you can use instead of Vivado to test out Vivado or any other industry standard compiler. So if you, I hope you guys can, I'm sorry, it's still not so. Yeah, I hope you can see the list of tools that's listed here. It's a free tool, EDA Playground, and you can see we have commercial simulators listed here. Aldegrivida, Cadence, Siemens, Questa, and Synopsys VCS, which are not the tools you will have access to anywhere else, which is quite a surprise for a free tool, right? So you are able to simulate your design on commercial simulators for free and get the output. So you are able to test your tools in these industry standard tools, and this is a quite a boon for anyone who is trying to learn the digital system design. And there are plenty of other tools as well. You can learn these tools as well if you want. Like we will be talking about very later, and USDs and Icarus Verilog's later as well. So yeah, this is an opportunity for anyone, and this has been there for a long time, just that people don't know about this and they miss out on this, and they like consider they it's a must for them to install Vivado when they're starting out Verilog, and it will rely like it will be a heavy load for them because they can't handle Verilog syntax and they have to handle Vivado installation immediately, which is quite a heavy task was to expect someone when they are just trying to start learning HDL, right? And you can also open wave simulations by using this option. I hope you guys can see this, like open wave after run, which basically allows you to run the tool in a specific simulator, and then in a pop-up, the underlying uh, simulated wave will be loaded. Mm, yeah, I hope you guys were able to see that. Yeah. So that's about EDA Playground. Mm, And the next one is server. So the next important skill you have to do. So first one is architectural significance and intuitiveness that you have to develop for well codes and how it will look on logic units. And the other one is simulators and how they handle output and how you are able to get relevant details from the output of commercial simulators and the waveforms. And the last thing that's really important when it comes to HDL is waveforms, not exactly HDL. When it comes to digital system designs, is waveform. I hope you guys have used some waveform viewers. I think GTK Wave is the preferred one or the Vivado. Has anyone used this Surfer waveform viewer? You guys can let me know via reactions or chat or whatever you prefer. Mm, yeah, that's fine. So yeah, as far as I know, many people haven't heard about this. That's why I'm bringing this up as well. So yeah, this is a better waveform viewer than GTK Wave or Vivado in all regards. But as far as I know, Vivado can't directly export to .vcd formats. So I usually use an LLM to create a custom tool to convert the Vivado waveform file to a VCD format. But this waveform viewer uh, is better in every way, and you can even use custom like decoding techniques. Like when you are trying to observe a waveform from a RISC-V processor, you can decode the RISC-V instructions quite clearly and display them as well. There are plenty of features in this waveform viewer you guys can check out. Like it's better than Vivado or GTK Wave. I hope you guys have at least used Vivado Waveform Viewer or GTK Wave. I am not preferring both of them because GTK Wave is not really cross-platform. Even when it's trying to work in cross-platform, it has some bugs. But this is a cross-platform waveform viewer you can even use in browser as well as install it offline as well. So that's quite an important tool. And you have to build the intuitiveness for reading waveforms because that's where you can actually figure out the issue because the generated waveform cannot lie to you. So you can detect if a test bench generated by LLM is lying or not by analyzing the waveform. So that's it. Like first step after learning the fundamentals, start your workflow in the browser. Or even if you are already working in the Vivado, this is quite a useful set of tools you can handle to like quickly check something that you have done, right? I hope that has been useful for you. And now we are moving to the next step, building the local lab. By building the local lab, I don't mean like you are building a fab in your house that's far exceeding what even Sri Lanka can do, or even somewhere in Asia. Like Taiwan, Taiwan is in Asia, so not exactly Asia. I don't think India even has its own app. So that's uh, our, that's not in our capability. We will focus on generating until the designs, right? So that's where we are focusing. And this is the stack of tools I recommend you guys to check out. Like at least check out. Like you guys can stick with the online tools I mentioned, or and Vivado and Quartus, whatever suits you. But these are the open source tools that I have used and considered to be useful among, like there are plenty of other open source tools as well, but I recommend you guys to check these out. Like Iverlog is a quick compile and simulator tool. Like uh, you should have seen it listed on like here as well, right? Gareth Verlog, that's the Iverlog tool. So you can try to run that tool on your Verilog file and quickly simulate it. And initially I did it for manual workloads. Now I use it for LLM workloads, right? So one thing LLM struggles with is feedback loop, right? So LLM needs to know whether it has done the right thing or not. So iVerilog can uh, take your Verilog file that your agent has written as input and try to compile it and give the errors to LLM, and LLM can iterate on it. So that's why these open source tools are useful because unlike Vivado can also be invoked via CLI, which I will discuss on the later techniques. Like you need to make sure that you have the reliable tools in your lab or in your local computer so that your LLM can quickly run these tests and get feedback that is reliable, right? Just by reading, LLM can't figure out every issue there is. That's the issue with LLMs. They are probabilistic machines and they can't figure out every architectural issue or timing issue, everything in the code just by reading the code file. So that's why we will be using these tools. Airlog is quick compile and simulator. Verilator is the fast simulation tool that's even being used in the industries. Just give me a quick reaction or chat if anyone has used Verilator before. It's fine if you haven't used as well. You can say no as well in the chat. I just want to feel that you guys are listening. Okay, fine. Yeah. So that's another tool I would encourage you guys to check out because it's a really fast simulator. And one of the things issues I have faced with Vivado is it's really slow, and Verilator can quickly simulate those things. It's not really a replacement for Vivado. I did not say that. You can use Verilator as a first pass validator, right? You can use Verilator with your LLM workflow in order to like uh, get your draft Verilog files to a certain state that is correct, right? And then you can put it in the Vivado and try to simulate it rather than going through that loop many times even before getting it right on the Verilator because Verilator can catch issues, uh, most issues, and Vivado has some more architectural fine tuning on top of it. So Vivado can catch other issues as well, but it will be less iterations on the Vivado because it's slow, right? So these tools can help you. And as I said already, Surfer is another tool. And Yosis is that synthesis and netlist tool, which is open source. That's quite a lot of engineering and effort put by the open source community. You guys can check that tool as well if you are willing to synthesize. But I I think from the workflows you will be dealing with in the university or with Xilinx FPGA boards or other things, you want to be needing UASys because AMD use its own compiling tool chain and it's not open source. So other than RTX 7 FPGAs, you will have to use Vivado or Quartus to synthesize for the FPGA. Yet you can know how to use these tools because this will be coming for the basic workflow as well when you are trying to integrate with tools like OpenRoad and other things. And the other thing is CocoaDB, which is a really good tool if you guys are into writing test benches with uh, like LLMs because it can write test benches in any language like any HDL and even Python, which is quite a good language that LLMs can handle, right? So LLMs can iterate quickly on test benches and most likely be correct. So you can try to use FuckoTV for your test benches because it's not really a limitation because that Python uh, test bench that is being written will eventually be converted into a Verilog or system Verilog test bench and then be run by a certain backend you choose. Like you can even choose Vivado or Verilator, but you have to install those tools so that the Python can access them in the backend and try to run them and give you the results. So it's a good orchestration tool as well as a tool for running test benches. You can check it out. Like it really makes your lives easier when it comes to writing test benches. And the other thing is quality of life improvements, which is uh, required mostly for like code quality. Like variable is a formatting and style check tool introduced by Google initially and now being maintained by community. So you can basically, I hope you guys know what code formatting is like. You basically format your code to be Verilog and system Verilog code to be properly spaced and indented so it can be read quickly or like it doesn't look clumsy. So it's also a good tool to keep in your arsenal. And then there's Litex. If you guys can time go through the Litex, it's like it's another Python-based tool which will allow you to program FPGAs and like quickly give you the tools to like deploy a RISC-V processor on an FPGA also. You can check it out on your own time. So those are the tools I'd like you to try when it comes to local lab. There are plenty of other tools as well. You can contact me if you want to know more. And then these are some of the tools I'd like you guys to keep in mind or like keep checking out when you are in, when if you are interested in digital system design, of course. Like so it is like LLVM based compiler infrastructure. Like this is for like current issues with the simulation tools, right? So current simulation tools and synthesis tools are not really uniform. Each of the tools are doing its own thing. So Circuit is trying to unify them all and trying to give a unified representation or like intermediate representation that can be used to design, give designs from any and all languages and compilers, right? So it's a like low level tool related to compiler architecture as well. If you guys are interested, you can check it out. Similar to that, there is Silicon Compiler, which is like Python first flow manager for like basically orchestrating all the tools for the ASIC work. Like and then there's open lane and open road. Like if you guys have heard about people trying to tape out actual chips like they have designed, you would have heard about open lane and open road because that's the platform they use to design those chips, like the open source tool they use to design rather than like Intel and AMD have their own tools. This is the community's tool to design our own chips, and Tiny Tapeout is the way we use. Like we submit it to Tiny Tapeout, and they uh, get all the submissions and put them in a wafer and print them out. So it's relatively low cost when it comes to printing out chips. So that's one of the ways we try to tape out chips, and our university people have done more than one chip as far as I know. And then there's LightX and Amaranth, which are Python-based tools as well. You can check it out if you want. But Amaranth is particularly good when it comes to trying to write uh, a digital system with Python. It converts into Verilog before synthesis, but you can understand Python in a better way, right? So if you are into Python, as I seen you, some of you guys mentioned Python as your favorite language, you can check out Amaranth. And then we come to the industry standard tools. I hope you guys have dealt with Vivado and Quartus, which are quite useful, but I don't like them because of the GUI. But you have to know that there exists a CLI option for them as well. So Vivado can be invoked via command line and called via batch mode. Like you can execute scripts on Vivado as well. You should know that because that's one of the ways you can automate workflows in Vivado. I am not so sure about Quartus, but you can try. There should be one. And I hope you guys know the distinction between FPGA and ASIC. Like FPGA, you guys program the processor into an existingly printed specialized like gated array, like programmable gated array. But in ASIC, you are basically printing the processor into a silicon, right? Processor or your design. You don't necessarily do ASIC in during learning because it's quite costly and it has plenty of workflows. But you should know about the tools that are used and have an overall idea about them because if you are into this field, you will be facing them eventually, and you shouldn't say that I haven't heard about these tools. So Questa, VCS, and Xelium are basically tools that are used in the ASIC workflow. And Synopsys and Cadence are the main competitors in that space. All right. So now that we have discussed tools that will help your LLMs, now we'll discuss about why LLMs fail badly, especially when it comes to HDL, right? So if you have noticed, there are not a lot of code written or published for HDL or digital system design, relatively low, right? And LLMs are trained on openly available code. So they don't have much knowledge probabilistically to write good HDL code because even the published like if you are publishing an HDL code for free, like just just think of yourself that you have learned high quality like styles and best practices on how to learn HDL, and you have designed a top tier module on digital systems. And will you publish it for free on GitHub? No, right? So everything that LLM has learned is from like learning attempts or like the code published by people who are trying to learn and did some coding randomly, right? So LLMs are not good at writing code that is related to digital system design at the first attempt. And especially it's an issue because like LLMs can't relate HDL with other programming languages because the paradigm of HDL is different because it's trying to relate concurrency and timing of the like primitives, which are logical units, AND gates, NAND gates, and everything, into a text file, which is hard to grasp around even for humans. And for LLMs to do that with pattern matching, that's not a feasible solution. So what we are trying to do is we are trying to overcome that via tools. And the another problem is like if you have used LLMs to like design GUIs, like if the LLM one shots the GUI and it looks good, then it's fine because LLM has like somehow did it. But if you try to edit a GUI, then you know that how the LLM is facing difficulty in trying to understand what sort of elements the GUI has and how it should be like tested and how it should be changed. So that's the issue with waveforms and debugging, right? So LLMs can't understand waveforms, so you should be on top of it and be able to like understand where the cycles are late and or implement tests in order to make it correct, right? So making the making sure the LLM understands the problem and setting up the feedback flow is the important task. And the other thing is LLM can completely miss your point. Like Claude Code missed my point here. Or the affirmation trap, which is the LLM can outright lie to you, like give you the nicest answer and says the test benches are passing and everything. And if you go into the test bench, it will have hard coded some values and set OK text as like I have faced these issues. That's why I'm telling you. I hope some of you might have faced these issues as well. I hope you guys can avoid these issues in the future by having efficient feedback loops via tools in the future. So yeah, LLMs can actually help. So you need to set up these your own reference like sources that are reliable so that you can do concept tutoring. Like you can write your own code and try to understand it with referencing your own like reliable course materials and YouTube transcripts that you have gathered. And also for boilerplates and scaffolding, right? So you can take an example project that they have already done and able to set up another new project based on that with LLMs quickly. LLMs can run tools and others better than trying to go through all of that one by one. And it can also produce a document for you to understand how it has been done so that you can change something or like make it flexible according to your needs. And also EDA support works, which are summarizing warnings. As I said, Vivado spouts out hundreds and thousands of warnings, which doesn't necessarily say what went wrong in your design. So you can get all those warnings and put it in an LLM and ask it what is the exact problem. And it doesn't always work from my experience, but it's usually more helpful than going through the stupid answers in the AMD forums or other forums. There are eventually correct answers in forums, but you will get a headache going through forums to yourself. So I recommend you guys to check check with LLM first. But if you haven't been convinced, then you can check the forums, which is should be the last resort, and it's a quite reliable resort because eventually you will be able to find an answer or ask someone who has more knowledge in the forums. And also design review questions, you can ask LLMs. Like LLMs are quite good at review, especially Gemini 3 models are quite good at architectural reviews. are quite well trained on like like trying to put up with architecture and how it should be optimized. Gemini models are quite good at that. And now cloud opus models are also somewhat good at that, but not really very scientific, but they are quite good at coding. So understand the strengths and weaknesses of models and try to review your source materials accordingly. And of course, this is one of the assertion ideas is one of the things that the industry is currently trying to do. So if you have learned HTL up to some point, you will know that you can write assertions, so, which is something you can do in software as well. Sometimes people call this unit tests, but they are not quite the same. So basically, what an assertion is, it, it's trying to confirm whether a uh, specific variable or value is equal to a specific value at a certain point, right? So you can write assertions on your system Verilog files in certain places so that you can verify that your wire or register stays within a certain value. Right? This is quite useful because you don't need to check waveforms when you are writing assertions, right? If you have written comprehensive assertions, which means you have covered every assertion there is possible for a certain digital design, then you don't have to check waveforms. You can just confirm whether your Verilog code is correct by assertions. But the problem is it always doesn't work that way because if you are going to write assertions to like reflect a golden model, you have to write millions of lines of assertions, which is not a feasible way. But some industries are trying to do this, but you can't always completely do 100% coverage of assertions. You have to pick and choose which assertions are more important. So in that regard, LLMs can help you. I hope you guys can look into this specific thing later when you have time because it's quite a useful thing when you are trying to use LLMs in your workflows. Don't try to write Verilog code first. Try to determine the assertions first and then write the Verilog code because otherwise, you don't understand what the design is, and then when you're trying to debug your designs, you will face many other issues, and eventually you will give up because your agent doesn't understand the design, and you don't understand the design, so you don't know how to move forward. That's the issues. And the next one is basically what the Mali earlier said, like prompt engineer, right? So the issue with prompt engineering is people have many ways to like make the LLM do everything, right? You can write the prompt a certain way and you can make the LLM do everything, but that's not the goal. You have to know, right? So I hope you guys understand the importance and significance of this issue because it doesn't matter if the LLM can do everything by consuming a prompt. It matters what you control, right? So if you can't change a certain thing down the line, you have to basically evaluate the prompt and try to like experiment how to convey the prompt in a way that it changes the specific thing later down the line, which is not a good approach because it's not iterative, it is prone to mistakes and it is prone to hallucinations. So the important thing you guys need to consider is you guys need to draft your Verilog file or your design file based on your idea of like planned architecture and then ask what is wrong with it, right? You guys have to review, evaluate an existing design rather than trying to delegate everything, like picking basically design every task into LLM, which is not what it's designed to do or good at doing because it's a probabilistic model and it doesn't always account for all the architectural decisions that a human can make. So that's how you make the LLM helpful. So I have listed here in a basic workflow, right? So you can write or revise an RTL, or HDL, which is basically the same thing. I guess some people have asked that as a question. So it's basically synonyms, but there are some nuances to it as well. But don't worry too much about this. RTL is register transfer logic, in the some people call it, but uh, they also call it synonymous to like HDL as well, hardware description language. So there are different levels to hardware description language, but we are not covering that here. But you can always ask an LLM, right? Let me know if you are not convinced with the LLM's answer, then I can give you a better answer. I'll try to give you a better answer. So yeah, you start with the HDL, like your own skeleton, and then use tools like Verilator or Variable to lint it. So these are deterministic tools, right? Thousands of engineers have put a lot of time and effort into the issues that come up when writing a Verilog and system Verilog code. And this tool will give you warnings. Why this shouldn't be like this, why this should be like this, these sorts of warnings. So you can lint it and get the warnings and try to use an LLM to fix those things, or try to prompt in LLM while we are getting this and try to fix those things manually. This is why LLMs are useful, because initially you have to go to a Stack Overflow or a Reddit post or a forum in order to hope to find the solution for the specific mistake or an issue that you are facing, right? Nowadays, LLMs can like infer the solution based on the millions of training data that it has, right? And also have back it up by some results if possible. So you can use the LLM as a turbocharged search engine and fix your issues and learn in a better way. That's the goal of LLMs that we have to use, because otherwise we are delegating our thinking to the LLM, which is not good for our brain. I will get back to this point later as well. So we have linted it and then we simulate it as I have already told you the tools iVerilog or Verilator, or you can use Vivado as well. And then inspect the waveform, of course, as mentioned in the previous tools, and then synthesize it. Whether if you are doing it for an open source IC like ICE tool or uh, uh, ICE tool, then you can uh, synthesize it using JOSIS. If you are using an AMD FPGA, you can synthesize using Vivado or Quartus if it's an RTX FPGA. Sorry, not RTX, it's if it's a Quartus FPGA. And of course, there are other steps like formal verifications that are done later down the line. You can learn those things and how to add them to pipeline later down the line. But these are the most important steps when it comes to learning how to write an HDL and design a digital system when you are trying to get started. Right. So this bad prompt and better prompt structure also like that's what told you already about how to basically plan the architecture and then design the test cases and stuff to verify the model, rather than trying to give all the decisions to the LLM, which is not good, especially when it comes to digital systems design. Right. So do not completely trust LLMs, because they are by design probabilistic models and they are prone to lying, when, especially when they are not trained on the specific material. Trust your own workflows that you have set up that have proper validation and verification techniques, right? So, which comes to working with agents. So, uh, I have initially preferred headless tools as well rather than GUI, because clicking through lots of buttons and setting menus in order to do a certain thing is not a like efficient way to do a repetitive workflow, right? So learn headless workflows, like learn how to invoke Vivado via CLI and run steps, and learn how to invoke other tools, like especially the ones I mentioned via the CLI as well, and have strict requirements about VCS and management, because if you are using LLMs, they are prone to messing up and you don't want to lose your whole work because an LLM decided to plan some entirely different architecture and try to rewrite every single file, right? So that's another thing here that you have to consider. And then there's testing and validation workflows done as manual as possible. What I mean by manual is you don't have to write every test and assertion and validation, right? You have to know what's being written, at least the test and validation, because main problem I see is even in my workflows, I don't have time to read through all the Verilog code that the agent has written, which is quite a lot of problem because we usually we can't as humans write more than 1,000 lines or even 1,000 lines of Verilog in one day. But agent can finish about 5,000 lines of Verilog in 1 hour or so, even 30 minutes if it's a fast agent, right? So we can't go through the implementation itself by ourselves. We need to have control over the testing and validation workflows at least. So that's another technique when it comes to working with agents, because that way you have some sort of a control over what's being written, right? So you can verify and the agent can iterate on its implementation until it fits the validation workflow that you have defined. And then, of course, you can try different HDLs that suits your mental model, because it's not an issue if you try other novel HDLs as well, because they also eventually like convert into Verilog before like being synthesized. As far as you know, all the modern HDLs do this because HDL Verilog is the only tool that's widely supported by all the synthesizers, and we don't have the existing like proper infrastructure to set up a synthesize synthesizing tool from scratch. That's one of the problems that the circuit compiler I told you guys earlier about aims to solve. But yeah, so you can try different HDLs and choose which one works for you best. And when it comes to learning, try to learn Verilog and VHDL. Those are the two main HDLs that people tend to use in the industry as far as possible. Uh, and it tries to stick with you because there are plenty of legacy code out there in Verilog and VHDL, and eventually you might have to go through some code. At least your LLM agent have to go through that code. So you need to understand Verilog and VHDL in order to like ask the agent specifics about what you are looking for, right? So try to do that. And of course, the another advantage of LLMs is visualization of results. LLMs can gather information and try to present them in a way that is convenient for you, whether it's flow charts, umami diagrams. Their timing diagrams can be represented in like wave DRO and timing diagrams like this one. You can go through this library and add it as a tool in your LLM workflow so that you can visualize timing in a better way. So, and of course, I hope you guys have heard of mermaid diagrams, which is just a flowchart representation, and which some of the LLMs use by default. As far as I know, ChatGPT and Claude use it by default. But yeah, you can go through it as well. And of course, you can create your own web app for your own visualization. If you like go through the Google AI Studio build gallery, you can see that people have created lots of web apps for visualization and their own sort of purposes. I have even created like risk V simulators just by asking for it in the build prompt, right? So there are plenty of tools available for you guys to learn, and that's the main goal here. You need to learn because you are not doing homework with agents. You are trying to learn the intuitive basics of this in a much convenient way for you. Like, you need to make it as convenient as possible. That's what LLMs do for you. So define your requirements and make it as convenient as possible for you, and then learn, right? And then we have the additional like if you guys have used agent harnesses like OpenCode or GitHub CLI or Gemini CLI, I think sub agents are an experimental feature in Gemini CLI. Yeah, you can try these things because when you're trying out larger designs or when you're trying to simulate something, the output logs are really huge and they can fill up your agent's context window quickly. Uh, Using sub agents, you can delegate the task to a certain agent so that it can do one simple thing and it won't fill up its context window. And give that only the results back to the main agent. This way you can like keep the main agent running for like however long you want, right? Even though there are compaction techniques available now, it's still more efficient to like keep everything within the context limit. So this is one of the things people use nowadays. And of course, additional feedbacks loops for iteration. Like always remember the most important thing when it comes to LLMs is feedback loops, right? You have to let your agent know what's going wrong. Otherwise, the agent will go free reign all over everything. And it's not good, especially for an engineering design. So the things I have said are not just some things I have done or like uh, just some things you have tried, right? These are being done out in the world, right? People have been using these open source tools in UC Santa Cruz and other universities, like highly regarded universities, in order to do this. Even though your course requirements doesn't specify these tools, you can still use Vivado and use these tools as like intermediate helper tools in order to make your iteration faster, right? And for instance, SPA has like do used LLMs to generate assertions, as I have mentioned earlier, in order to find the real risky bug. So the lesson is like verification support is really something critical that people have like faced for a very long time, because writing like many assertions is not a very good human handled task, right? So you are prone to missing certain things, and it's a really huge list. So people can use LLMs to review the design, because LLMs are very good at large context when it's within the context limit. So LLMs can use iterative loops to identify issues within a section. So that's how Princeton SVA has succeeded in doing this. And of course, as I mentioned earlier, like our UOM people have designed and tape out chips. Sorry for that. Yeah, chips in tiny tape out. Uh, so they have fabricated chips. So it's not something we haven't done before. I'm telling you guys so that you can know that this is possible even within your university time. So I hope if you are really interested, you guys can look into these things. And this is another thing I want you guys to look into. This is before 2 years, like a paper published on 2024, like how NVIDIA was trying to use LLMs, even when the LLMs were not good back then. They had proper feedback loop set up to write a very rigid workflow and the Verilog code of the module. And then how they also had workflows to analyze the waveform tracing via like abstract syntax trees. Yeah. If you guys are interested, you guys can look into this paper, like how you can basically use LLMs in any engineering workflow to scale up, because NVIDIA has really scaled up their workflow using LLMs, because otherwise you wouldn't be able to put this much powerful chips this much faster, because they are at a bigger leap and they have bigger lead than any others in the industry. So we need to learn from the best, right? So you can look into that as well. And of course, Tiny Tapeout has like workflows for LLM assisted tooling, right? They have the PGA designs with students under 90 minutes with LLM assisted tooling, as well as I think, as far as I've seen, there are GitHub repositories with template LLM assisted repos, which basically you can clone the repos and try to set up your design within minutes, which is something only enabled by LLMs, right? So you need to make sure that you are using the LLM for the useful things it can do only, not to replace your thinking. So for setting up like all the hard parts of the tool chain and all, to solve all the like unorthodox ways that tools have been handled by everyone in the community, and all the like foot guns exposed by tools. You can use LLMs to handle them, but you need to keep the main picture in mind. You need fundamentals and you need to be in control of the design. That's the main goal. So don't forget that, right? So as a final takeaway, LLMs do not replace digital design fundamentals. They raise their value, right? So you need to know the fundamentals in order to know that you know that it's lying to you, right? The LLM can design an acceptable architecture, but in hardware, everything is nuanced, right? You need to know timing and you need to manage concurrency and everything. So you need to know the fundamentals and architecture explicitly and define them accordingly with rigid constraints so that LLM can help you. Otherwise, LLM's just going to fool you and you are going to get fooled. So this is one of the except from one of the articles I wrote. So it still applies. This is from an year ago. So use AI like a turbocharged browser, right? Great for searching, researching, learning stuff fast, and doing workflows that was otherwise like repetitive or like cursed, right? So, but don't let it do the actual work for you. Like that's like getting a gym membership and watching someone else lift. Like if you stop using your brain, it stops showing up for you. Like, uh, even if it's your favorite programming language, you can feel the effects of like not writing Python and letting LLM do it for you by trying to open a Python file and trying to write something basic. You can immediately feel it, right? Just try to take a pen and paper and try to write something. If you haven't written for a long time, it will feel hard as well. Even if you have, even if you are used to writing like thousands of lines per day previously, right? So you need to show up. You need to do the actual work. That's the final takeaway. I hope you guys were able to get some use of out of this. Let me check the questions. Yeah, I think I have answered one of these questions. I don't think I am the actual person who can give you an idea about job options in FPGAs, but FPGAs are critical tools in current industries for high performance compute. So everyone is using FPGAs for all kinds of things, especially in robotics and in even in LLMs and in acceleration workflows when trying to use like a certain type of calculations faster. So FPGAs can be programmed with really specific architectural accelerators. So in those kinds of jobs, FPGAs are being used. I hope that what you are asking. So most related to academia also, you can go to academia research, which is something I did in my intern. So I was going to an internship, which is basically a research assistant for accelerating a specific robotic workflow in an FPGA. And I think there are plenty of research positions in industries as well. And if you're going for something more nuanced than that, then there are plenty of opportunities in vision as well for FPGA, like machine vision and like anywhere you have a specific acceleration need, you can use FPGAs. And I think there are also opportunities in networking and telecommunications as well, but I'm not up to speed with them. Maybe someone else can enlighten me to with those. Yeah. Let me know if that's not enough. Yeah. Are there any other questions? So was this useful for you guys? Yeah. Thank you for the comment. Yeah. If you guys have any questions, you can ask. Otherwise, we can wrap up in 25, I guess. Yeah. I'll wait for 3 minutes. You can open your mics and ask as well if you prefer that. Any applications for FPGAs in BME? Yeah. So as I said, like BME has a lot of robotics applications as well, right? And I remember seeing genomics decode application. I don't know. Like, I think, as I said, like, even you can, like, uh, try to invent applications, right? So, as I said, FPGAs are highly flexible parts of technology that you can craft any sort of architectural accelerator into. So, if you have any need of accelerators in BM, you can use it for them. Even if it's, I think I was looking into an idea called soft robotics. Like, I think soft robotics is also something BME guys also look into. Like, uh, there are plenty of high complex computing in soft robotics that you can try to accelerate with FPGAs. And there's also the aspect of vision, like trying to like decode images and try to identify or classify diseases, which can be accelerated with specific FPGA accelerated according to need. Like, let's say you are going to try to deploy a certain brain scan, like a classifier model for brain scanning in a rural environment, and you need to run it on a low compute and low power consumption device. Then you can design that design a processor, custom processor that can run that model in such low power using FPGA. So that's something I can think of. I'm sure there are plenty of other applications as well. I hope that was what you are asking. Let me know otherwise. Yeah, I guess that's it. Yeah, sure. Yeah. So thank you guys. Thank you for putting your time into this. I hope it has been somewhat useful for you. Good night.